Hi guys, can I get a sound check?
Works.
Great.
Hello.
Thanks, guys.
You're loud and clear.
Awesome. Thanks. All right. Where were we? Just give me 1 second, guys, to get here. Get my crap together. Let's see. Okay, let's see. All righty. Okay. Have you guys had much luck with, or have you guys been trying the homeworks and stuff?
Yeah.
Some of you.
Yeah.
So I thought, Kevin and Melvin, I think, were in my office hours, and they asked some, they had some different kind of questions about the homework. There was one problem in particular that we were talking about that I thought would give you guys some insight. So I thought I'd just go over that. It's something that confuses a lot of people. So, I was going to kick off at that. Hopefully it'll illustrate the concept of, setting up this iterative procedure for coming up with the operating point of a circuit, and then sort of lead to small signal and all that stuff. So I was going to go through that with you guys first, and then use that opportunity to also talk about, what we're doing in general. Okay, so the problem that in particular that we talked about quite a bit, I think with Kevin, was problem 4.22B. I mean, yeah, we just talked about the B version, but it was 4.22. So in that problem, we had there's a bipolar transistor. The collector is hooked up to 2 volts, and the base is connected to the collector, and there is a resistor hanging off the emitter. So this is the emitter, this is the base, this is the collector. All right, and there's this resistor. It's like a 1 kilo ohm resistor. And they give us some transistor parameters. So they say, okay, for Q1, they give us an I sub S, which is, what is it? 8 times 10 to the minus 16 amps. They gave us a beta of 100. And there's this VA equal to infinity. This is let's just ignore this for now. We'll talk about it in today's lecture, but you can ignore it for now. Whenever, anyway. So, okay. So what they are asking for is, build a small circuit model of this. Okay, so what is the small signal model? Well, let's draw it first. Let's draw the small signal model first, and then we talk about how to get the different parameters. So the small signal model, we've got so we have the base, there is a resistor R sub pi in the base. And there's a current source going to the collector. And this is G sub M, V sub pi. And there is a, the emitter. So that's a bipolar. So this is small signal model of Q1, which is the
kids messing.
Sorry, question?
Would the emitter doesn't have the resistor in the small signal?
Yeah, it would. Let me just leave it at this level, and then I'll come back and hook up all the stuff around it.
Okay.
Just the hookup of it is gonna lead to some questions for you guys, but I want to first go through figuring out the bias point and all that. So go discuss that for a few minutes, and then we'll come back around. So right now, I just want to do, this is a small signal model of Q1 of just, as Darren mentioned, this is just for the transistor. I don't have this yet. I don't have this yet. I don't have this stuff yet. So I just have the transistor, okay? And so when it says build the small signal model, I have to figure out how to connect all this stuff. But then I also need to so 2 steps. So answer has, let's say it has 3 steps, okay? Okay, so step 1 is, well, it already says step 1. Find bias points. What does that mean? Well, to figure out these parameters, and I'll talk about this in a bit, we need to figure out essentially how much current is running through this device, okay, the way it's connected up. So we need to find I sub C and or VBE for Q1. Okay, so that's step 1. You figure out what's I sub C, what's all the voltages of this guy. Once you have I sub C, okay, so step 2, calculate GM and R sub pi, okay? Then once you have I sub C, it's pretty easy to calculate those 2. And the equations are, because the equations just say GM is I sub C over V sub T. And, V sub T is just 26 millivolts at room temperature, so it's a constant. And R sub pi is just this G sub M over beta. And they gave us beta as being 100. So once you have I sub C, you're pretty gold. You can just, it's just a multiplication division, and you get the values for G sub M and V sub pi. And then lastly, you go take step 3, which is draw out the rest of small signal circuit, which are, what are these? So these things start doing some funky stuff when we're in small signal, because in small signal, we're only looking at changes, not whatever. We were sort of stripping off whatever is constant and only focused on changes, okay? So you got to do those 3 steps to answer this question. So let's do step 1, which is probably the majority of what I'm going to spend the time on, okay? So we got to figure out, this is our circuit, okay? And so we got to figure out like what I sub C is, okay? So let me just copy and paste it. It's a little easier. Okay, so let's see this. So ISA for this problem, and so let me just say this. So we have I sub c for Q1 is I sub s exponential of VBE over VT. So that's like a very basic equation that we've gone over and over again. We know that. Okay, so they gave us I sub s up here. Okay, we're good with that. And VT is 26 millivolts at room temperature. Now the question is, what is VBE when we look at this? Okay, so the base is connected to the collector. Okay, and the collector is hooked up to 2 volts. So the voltage at the base is 2 volts, right? So this is 2 volts, right? Everybody, any questions about why that's 2 volts? I mean, just shorted to a 2-volt battery. It's already good to go. The problem is we don't know VE. Right? VE is just hanging in the breeze over here. And so the question is, like, how do we figure it out? Okay. Otherwise, because we need VB, we need VBE. The definition is VB minus VE. So, you know, we've got 2 volts minus question mark, right? So we got to figure out what this VE is. Okay. So we've got to solve, there's 2 things that determine the current in this, the current and therefore the voltages in this circuit. Okay, one of them is this equation. Okay, depending on the VBE, you get a certain current going through this guy. All right, so that's one. So this equation here. The second equation that determines this is you get that current going through this resistor. So that creates a voltage here as well. So if I look at, so this VE, one is defined by how much current goes through here, and you know, and vice versa. That voltage of that VE determines the current. So it's what sort of a, it's like something that's got 2 dependencies, and we got to figure out what that is. But the second thing is we've got the current through this resistor. Okay, so that's the I sub E, the emitter current. So the voltage at E is also equal to ground. So this is this point. So I'm going to just write everything up. So 0 plus the voltage through this resistor, which is just I sub E times 1 kilo, or IE times 1 kilo. Okay. So VE is equal to this. And if I was gonna, I'm gonna just rewrite this. Okay. So I'm gonna rewrite this as I sub s exponential of VBE. I'm gonna write as 2 volt minus VE over VT. Okay. This is V sub B, this is V sub E, so together they make up VBE. Okay, and I'm going to take this thing and rewrite it, and to pull out VE. Okay, and I'm going to get 2 volts minus VT natural log of IC over IS. I just took this, rewrote it like this. Okay, I'm just moving stuff around, took the natural log. So I've got, so this equation 1, and I've got equation 2. Okay, so this equation 1 is sort of set by the 1 kilo ohm resistor. is one way to look at it. And equation 2 is set by our transistor Q1. Okay. So together, these two tell you what happens here. Okay. So if I solve these simultaneously, and by the way, so I'm going to go back here and make another statement, is that I sub E is equal to I sub C plus I sub B, and I sub B is equal to I sub C over beta. Beta they gave to us is 100. So I sub E is equal to I sub C 1 plus 1 over 100. And so I'm going to claim that I sub C, because this is like, this number ends up being 1.01, which is almost 1. So it's I sub C is approximately I sub C. Okay, so I'm going to go call this I sub C. So I have basically two equations. They both have V sub E, and they both have I sub C. So if I simultaneously solve these equations, I would get I could get I sub C and V sub E. Got two unknowns and two equations. Okay, I'm going to take a breather there. Any questions about what I did so far?
Professor.
Yeah, what's up, Nelson?
Could you explain how you went from what is it? The VE. How did you get those the equation where like 0 plus I plus 1 kilo?
This one?
Yeah.
Okay, so it's just KVL. So if I look at the KVL at this point, it's basically, this is ground, so this is 0, plus I have an I times R through this resistor, gets me to this point, which is VE. And that's, if you can think of this VE is in relation to ground. So the KVL would be from ground going through this resistor back to ground.
Okay, I see. Yeah.
Got it. So I wrote the 0 just to make it sort of clear that we're going from ground plus the resistive drop across the resistor.
Okay. And then I noticed you crossed out IE to get IC.
Yeah. Well, okay. So the reason is, what I want to do is I want to create a situation where I have two equations and two unknowns, right? So this is the emitter current, okay? And this is the equation for the collector current, right? So somehow I got to go from emitter current to collector current here, so that I have collector current here and VE here, VE and collector current here. I can do two things. I can either plug this thing in. Did you see how I got this?
Oh.
So we have an equation for the emitter current in terms of the collector current, right? And the base current. Do you remember this?
I believe so.
Okay, which is just simply that if you have, so this is the base, this is the collector, this is the emitter. It just says if you have a current going through the base and a current going through the collector, then the current coming out of the emitter is just the base current plus the collector current. Do you remember that?
Oh, yeah, I remember that, yeah.
Yeah, so that's all I'm saying here. Okay, and then furthermore, we remember that, I don't know if you remember, but that I sub B is I sub C over beta.
Oh, yeah, I remember hearing about that. Yeah.
Okay, so I plug that. So I plug that. These are like good, like memorize these. I guess there's no other nice way to put it. You only have a few things you need to memorize. I would memorize this guy, and memorize these relationships. And, you know, or little, these guys is also good to memorize. Again, you always have open book, you know, open internet, open everything. But if you remember these few equations, you'll just get to the solution faster. So it won't have to be flipping around looking at stuff, what to do. So anyway, if we have, I have,
Professor,
yeah, go ahead.
I just had a quick question about replacing I sub E with I sub C. Would it be wrong to do 1.01 I sub C, or is it just that the difference is so small that it doesn't really matter?
Yeah, I think absolutely correctly would be 1.01 I sub C. So that would be like, you could do that. That's the way to go.
Okay, but it's just they're so close.
Yeah, they're so close because, you know, in real life, when you're doing real engineering, like the kilo ohm, when you get a kilo ohm resistor, it's never quite a kilo ohm. They're like the best resistor you're going to be able to buy is plus minus 1%. So it's already a 1% variation in this. The, you know, the I sub S value by itself is going to vary. It's not going to be, this is like, it'll be 8 times 10 to minus 16, or maybe 10 times 10 to minus 16, or the manufacturer will tell you that. So there's like a 1% variations floating around here anyway in a real design. But we could have easily done 1.01 I sub C. So you're right. But I was just being lazy and saying it's approximately. You'll see that a lot when people say the emitter current is approximately the collector current, just to make life easy.
Okay.
Yeah. Going back to, who was I talking to? Nelson?
Yeah.
But did that answer your question about how we sort of crossed this out? Because I just went through.
Yeah. You basically just substituted the equation with the beta and just put it into here. That way you can kind of solve it for that.
And like Darren said, if I was going to be absolutely like correct, I would say IE is equal to 1.01 I sub C, and, you know, plug 1.01 I sub C into this. But like I mentioned, I'm just doing this wiggly thing to say it's a 1.01 is approximately equal to 1. Okay, which you would not be incorrect for doing 1.01 either. So, okay.
Yeah.
Okay. Any other questions?
Is the second equation from the IC equals IS
Yeah.
exponential?
Yeah. So what I did was, so let me do that the long way. So I'm going to copy this over. Okay, so so this one is just something we should memorize. It's the word of a higher power. This like is a given. We never, as long as we are in forward active operation, we can use this. So we got that. Did you see the step from VBE to this guy? I just said this is the base emitter voltage. So the base is shorted to 2 volts. Okay, so that's where that 2 volts comes in. And the emitter we don't know. So I left that as a variable. Okay, so that's how we ended up from here to here. You good with that?
Yeah. Because 2V is just VB.
Yeah. And so all I did was, let's see, what did I do? I would do, so exponential of 2 volt minus VE over VT is I sub C over I sub S. I'm just moving stuff around here. Take the natural log of both sides, and I end up with 2V minus VE over VT is equal to natural log of IC over IS. And then I move, so I do VE is 2 volts minus VT natural log of IC over IS. Did I do that right? Yeah. So I'm just moving stuff around. I just want to get two. I just wanted to get 2 equations, both of them in terms of VE. So it's pretty obvious what we're doing. That we have these kind of 2 unknowns and 2 equations. So I just moved it around. Does that make sense?
Yeah, that makes sense.
Okay. So, okay. Any other questions, guys? Okay. So now now we've set up the problem, and okay, great. We've got 2 equations and 2 unknowns, and in most other classes up to this point, especially in math classes, right? Usually you just go about, you got 2 equations, 2 unknowns, and hey, like we can solve that like a closed form solution, because that's how they set up life for us so far. I don't know if you guys have ever seen 2 equations and 2 unknowns before this class that didn't have a closed form solution, right? But the unfortunate truth is that when you have, you know, one of the equations has this sort of like a natural log-ish kind of thing, like somehow taking this, putting I sub c in terms of VE and plugging it in here, you're going to have a VE, and then you're going to have a VT natural log of something with a VE here. You're just not going to get a closed form solution for this, okay? Although you do have 2 equations and 2 unknowns. So what you do is you're trying to like come up, you're going to try to like, you have a couple of options on how to solve this thing. And one of them is to start guessing at what VE, like come up with a VE number, like a good starting guess for the VE number, plug it into either equation and see what you get, and use the result, the difference. Your first guess isn't going to be right. You would, you know, try to figure out what the differences are and use that guess to come up with a second guess and plug it into the equations again, and so on and so forth until, you know, it's sort of an iterative procedure, which we've seen earlier, and you see it in the homework problems. Okay. So why can we get, and why can we even take a guess? Here is the question, right? The reason we can take a guess is because VBE, the range of reasonable VBE values is fairly limited, okay? So like always, whenever your device is in forward active mode, so reasonable range of VBE values in forward active is like, I don't know, 600 to, let's say, actually, I'm going to even tighten it up a little bit more. I mean, you might go below 600, 650, 600, but I would say it's even more limited, 650 to say 850 millivolts. Okay. Why is that? Why is there a limited range? I think we talked about it a little bit. So the reason is you have this type of characteristic where you have, if we draw I sub c is I sub s exponential of VBE over VT, we get this, like, you know, we get this exponential characteristic, and when this thing is on, this voltage isn't going to vary very much. It's going to go from 650 to 850 millivolts. It's not going to be like 2 volts. It's not going to be like 300 millivolts. Okay, so you can take a pretty good, you can get a guess for VBE somewhere between here. Okay, for VBE for this, and plug it into this equations as a good starting point. So it's not like this could be, VE could be anything. So remember VBE, so as I wrote here, is VB minus VE. VB is given as 2 volts, right? So it's 2 volts minus VE. So VE is 2 volts minus VBE. So I can come up with an initial guess. I don't know, I'm going to guess that VBE, so guess 1, VBE is, I don't know, 750 millivolts. It's always my favorite first guess. Okay, meaning that VE is going to be 2 volts minus 750 millivolts is equal to 1.25 volts. I plug that into here and here and sort of calculate what I get for I sub C. And like, depending on what that value is, I adjust either, I say, oh, 750 was too high or it's too low. So I'm gonna go higher or lower. Okay. So that's a numerical iterative procedure. Okay. But what I wanted to do, so any questions about that? Come on, guys, give me your questions. It's either now or like during the quiz next Thursday. It'll be too late. I'm sure there's at least some confused people. Okay, so you can always come back and ask more questions later. So let's keep going here. Okay, so let's call this a numerical iterative procedure. I said there's 2 ways to try to solve this thing. So this is like method 1. Okay. So, Arthur, what's your question?
So for the first method, it's basically an assumption, right?
That assumption is just gives you a sort of a seed value. So your starting point, your assumption is just, you're taking a crack at it and it's seeding the value. But as it's like, you pick, you could pick 750, you could pick 800, 700, 650, whatever you like, 850. And then that's your seed value for this feedback loop. And you plug it in and see the differences between the results from these 2 equations. And then you either go lower and then do another iteration or go higher and take another iteration. You just got to be smart about the way you're iterating. So the assumption is your seed value into these assumptions. Okay. You're good, Arthur?
I think so.
Okay, so it's an initial guess. Okay. All right, so that's one option. Okay, the other option is doing it graphically. Okay, that's what I was going to show to you guys today and see if it may help you guys get a better understanding or might confuse you more. But it's just doing the same thing. So if there's a graphical method of trying to solve these 2 simultaneous equations. So what's that graphical method? Well, we put them both in terms of the same thing and we graph these equations, right? Where the 2 equations cross, the 2 graphs cross, is the only permissible value for the circuit. Okay, so let me do the first graph. So we have this I sub C is I sub S exponential of VBE of Q1 over VT. Okay, and that's going to look like our familiar expression. It's going to look like this exponential curve, right? Okay, so that's this guy, or it could be this guy, right? So that's one. Now I gotta graph this thing here on top of this. Okay. Now there's a little bit of a complication. Is that this equation is in terms of VE. I gotta put it in terms of VBE because that's the axis I'm plotting it against. Okay, so basically I have V sub E is I sub C times 1 kilo ohm. And then V sub B E Q1 is 2 volts minus VE. So I sub C is 2 volts minus VBE Q1 over 1 kilo ohm. I got to draw this here. So this is VBEQ, right? And I want to draw this here on top of this graph and see where the two cross. Okay. Any question about that?
Professor, so basically you just graph them and then see where they intersect?
Yeah. Yeah.
Oh, okay. That doesn't
So,
seem
yeah. So let me show you then the only, so let's see what the graph would look like. Okay. So we've got this guy, okay, which is a resistor. So let's look at what this would look like. Okay. So remember that if we had a resistor, so a resistor has a graph like so, it should be going through 0, right? And so, and I and V. And so this equation is I is equal to V over R, and this slope is 1 over R. Okay? So that's this equation, I is equal to V over R. Okay, let me rewrite this as 2 volts over 1 kilo ohm minus VBEQ over 1 kilo ohm, or 2 milliamps minus VBEQ1 over 1 kilo. Just rewriting it. Okay, so basically this looks like an I offset minus a V over R, right? So that's what I'm trying to get to. Like, what does that look like? Okay, so far I've got V over R. We're all familiar with that. Okay, but look at this. It's minus V over R. So what does that look like? Well, I is equal to minus V over R is going to look like this. It's going to go this way. Should be going through 0 here. Okay, sorry. So everybody with me?
Yeah.
Okay. And then on top of that, I got this offset. So what does that look like? Well, if I want to draw a I is equal to I offset minus V over R. If I add an offset to this guy, I would I would move this guy, whoops, and make it more, give it more of an offset. So I would get an offset. So it would look like this, right? This is I offset. And this curve is 1 over R. So I get a line going like this, with the intercept being this offset value, and the slope being 1 over R. Okay, so if I was going to go back to draw it here, I'm just going to copy and paste so you can see everything. Try to anyway. Resize this guy a little bit. Okay, so if I was gonna draw this on top here, remember that what I'm actually trying to draw is 2 milliamps. So I'm gonna copy, let's copy that as well. So my I in this case, this is I offset. And 1 over R is the resistance. So what I would do is I would have this would be I offset or 2 milliamps. And I would, let me draw it with some other equations. I would get something like something like that. Okay, so this guy in red is my sort of, you could think of sort of transistor equation. So that's the relationship between the current and voltage set by the transistor. And this orange line is the, if you can think of it as the resistor equation. So that's the relationship between voltage and current that is set by the resistor. So we have a transistor and a resistor, and there's a current going through the transistor, a current going through the resistor. Those two currents have to be the same. There's no other place for the current to go. So meaning that both of these have to be true. And there's only one point where these two lines cross. Okay. And that's the point we're looking for. Okay. So I put this stuff in. Let me see if I can do this for that. Stop here. I'm going to stop sharing that. Okay, I'm going to share. Okay, so you guys should be able to see like an Excel sheet, right?
Yeah.
Yeah. So what I did is I just put these two equations in a graph. Okay, so here's so I got VBE here in the horizontal axis. Then I made the exponential equation in blue, and then I put the resistive equation in orange, and put them on top of each other. It doesn't quite look like what we're looking for. It's because it's zoomed out. So I zoomed in just from 0 to 0.8. Notice I'm going from 0 to 1 here. So I just went from 0 to 0.8. Okay. Notice that the orange is sort of, this is the resistor. And it's going to get to 0, I don't know, somewhere out here in the graph. Okay. And it's going to 2 milliamps over here. Okay. So where these guys cross is, around 0.73 volts for VBE and a collector current of 1.27 milliamps. Okay. So and that's the only permissible place. It's, you know, it's, yeah, close to 0.75, but it could have just been, you know, that was just a guess, you know, that's where I started everything from. It could have easily ended up being 0.7 or 0.68 or whatever. Okay, so this is the point we're looking for, where these two intersect. And sort of we're doing the same thing when we're doing the numeric estimation, is say we, you know, come up with a starting point here. We wouldn't come up with a starting point of 0.3 for VBE, because we know that's like not a reasonable value. You can just see it from the graph here, right? Reasonable numbers here are from like 0.65-ish to maybe 0.8-ish, right? Sort of, the reason is this curve is because it's exponential, the signal is the I sub c is very, very low below 0.6 and very, very high after 0.8. I mean, this, anyway, they just look at this guy. This is zoomed out a little bit at 1 volt. This is already at like 40 amps coming out of this transistor, which, like, unless you're making power circuits, ain't gonna happen, right? So we're really like talking about, these are reasonable estimates. That's why I'm saying, like, the reasonable estimates for VBE are between 650 and 850. So like somewhere around here, okay? Because it just takes off like crazy after that, and before that you're just very low currents. So, you know, it's possible to use the circuit out here. It's possible to use the circuit here, but it's, you know, rare. Like if you're using, I don't know, like making a pacemaker, you might run it like this. And if you're using a power amp, you might want to run it like that. But most of the time we're here. So you would pick, I don't know, a guess, let's say you picked 0.7. You'd end up getting, you know, whatever the heck this is, 394 microamps for the value coming out of the transistor. And you would get 1.3 milliamps for the value coming out of the resistor. Those obviously aren't the same thing, and it looks like the value for the resistor is quite a bit higher than the value for the transistor. So you go, okay, so I need to bring up the value for the transistor. Let me pick a higher number than 0.7. Let's say you pick, I don't know, you go nuts and you pick 0.75, right? You go up here, okay? Now you get 2.7 milliamps for the transistor and 1.24 for the resistor. You go, now I went too high. Let me go split the difference. And you kind of come down here. So when you're doing the iterative procedure, that's what you're doing with your equations. You come up with a beginning point, compare the two values, and depending on the difference, you pick the next point. But you could have easily done this graphical approach, but that's what you're doing numerically in that first case. Okay, so this is an actual analysis technique called load line, LOAD line analysis. You know, some people use this. It's a legit way to do it, but you know, you still have to come up with these equations for the two equations we talked about. It's just a matter of how you're choosing to do a numeric analysis. Okay. So the upshot is we've got two equations and two unknowns. There's no closed form answer for those two equations and two unknowns. So we have to use numerical models analysis to come up with an answer for that system. And there's a bunch of ways to do that. One of them is just estimate numbers and use it numerically, or you can graph it, or there may be a million other ways to do numerical analysis, but those are sort of what's typically used. Okay. So again, I'm hoping that this graphical model might, for some of you guys, maybe makes more sense. Hopefully that, you know, what we're doing there. But you know, I was hoping I was going to show you guys that, like what we're doing in terms of numerical analysis, and also just from the graph, you know, because I keep drawing this exponential curve. But from this, when you're drawing something like this, from like this, you really see why our initial guess for VBE should be between 650 and say 850 or 800. Because again, it's a really, it's hard to draw this exponential curve by hand to show how small the values are below 650, 600, and how huge the values start getting once you get past 800, 850. Again, this is exactly the same curve. I've just zoomed out to 1 volt, and you can see how fast this thing's blowing up out here. So it's really this range of VBEs is what's reasonable. Okay, any questions about that, these graphs and Excel sheet before I go back to my hand drawings?
I had a quick question.
Yeah.
So we're looking at this graph. This is like another way to do it. So when we do get like that cross, it would be 2 points, right? It'd be VBE and then IC, and then that would be considered like the operating point, I think is what it is. Yeah, operating point.
That's right. Yeah.
Okay, so then okay. Thank you.
Sure. Yeah.
Professor?
Yeah.
I don't know if this already been mentioned, but when you're okay, so I guess whether you're graphing it or solving it equation-wise,
Yeah.
what exactly are we solving for in terms of like?
Yeah. So let's take you back. So start sharing now. Let's see, how do I get out of this point? Let me see. Okay. Let me try. Just give me 1 second, guys. I gotta figure out how to do this. How did I lose my Zoom? There we go. My share screen. Start share. Yes. So no matter what you're doing, the be all end all, the only thing you're doing is you're trying to solve these 2 equations. These 2 equations and 2 unknowns. And these 2 equations and 2 unknowns came from the fact that you have a transistor and a resistor. Okay. The 2 equations, one is for the, so you got a transistor and a resistor. There's a current through the transistor and a current through the resistor. They have to be the same by Kirchhoff's current laws. This guy's pumping current into here. This is pulling current out of there. They have to be the same. Okay. So that's the unknown. Okay. Well, that's one of the unknowns is the current. The second unknown is this voltage here. Okay, which is V sub E. So we got I sub C and V sub E are the 2, I sub C and V sub E are the 2 unknowns. And the 2 equations are essentially the equation for the transistor, which is this exponential guy, and then the equation for the resistor, which is just your, V is equal to IR kind of thing, like this guy. So what you're really doing with both of those techniques is you're trying to solve these 2 equations and 2 unknowns to get I sub C and V sub E so that you can get your small signal parameters. So you want to find out, what you really need is just really honestly just I sub C, okay? Because you want to, once you got I sub C, you get your small signal parameters, okay? But anyway, you got these 2. It's because of this natural log, because the equation out of the transistor is this sort of exponential, we're not going to get a closed form solution from the 2 equations and 2 unknowns. So we've got to come up with some other way, either graphical, some kind of a numerical analysis model to get this result. So we're trying to find out I sub C from that. Does that make sense, Nelson? Did you ask the question, Nelson?
Yeah, that makes sense. Yeah. Basically, you're just solving for IC.
We're just solving for I sub C. Yeah.
Got it. Okay.
Sometimes you might be solving for VE too, as you'll see in Depends on which one you need.
Oh,
So,
so in that case, you,
yeah.
Oh.
For this problem, you just need I sub c.
okay, but basically, if you had to solve for another variable like b sub e, then in that case, you would probably make the two equations in terms of IC, right?
Well, either way, you end up getting v sub e too, right? Because v sub e is when we get VBE, that crossing point gives us VBE, and v sub e is just 2 volts minus VBE.
Oh, okay, right.
So out of that graphical technique or the numerical technique, you get basically both unknowns come out. Both v sub e and I sub c, you'll have values for both. And then it just depends on which one you need to use for the rest of your problem. Okie dokes. Any questions, guys? Okay, so once you got that, so now you guys remember off the graph, I read, just I'm remembering what I read from the graph, or numerically if I solved it, VBE was, what was it? I think it was like 0.73 volts. And, I sub C was 1.27 milliamps, okay? So now, this was just to get catching our breath. This was just to the step one, which was the big step, which was to find the bias point. Now we found it, okay? So step two is really, really easy to get G sub m and R sub pi, because you're just multiplying the two numbers, right? So this was step one. So step one, the result was I sub c is 1.27 milliamps, and VBE was 0.73 volts. Step two, we got G sub m is I sub c over VT, or 1.27 milliamps over 26 millivolts. And that gives stuff down. That gives you 48.8 millisiemens, or another way to write it is 1 over 20.5 ohms. Okay, and then R sub pi is beta over G sub m. So beta they gave us as 100. So it's 100 over this guy, 20, over this. Don't make this mistake. This is the easy one to make. I almost made it right there. 1 over 20.5 ohms. So it's equal to 2050 ohms. Okay, so step two was really fast. Any questions about that? And just memorize these. There's just no other way to put it. Simple equations, you guys can memorize that, or write it, make a cheat sheet or whatever. Okay, so that's step two, easy. Step three was to draw the circuit. Okay, so let's draw the circuit. I said the small signal looks like this. So I'm going to dump that down. Okay, except R sub pi is, we have a value for it, is this 2050 ohms. And G sub m, we have a value, whoops. We have a value for it, it's this, whatever, 1 over 20.5 ohm V sub pi. Okay, so we got those values. Now, so we plug those values, but now we also have to draw the rest of these connections. Okay, let me copy this, clean that over. So this is the large signal. This might be another point of confusion. Let's see if I can paste over here. Okay, so we want to basically, this is the large signal, and we're going to draw the small signal. Okay, so we really have just kind of maybe a couple of rules for going from large signal to small signal. Then they're really the same thing, is that we're only carrying over whatever changes to the small signal, because all this stuff, the bias point already has all this information, like this 2 volts, the bias point already has that information. We use that to get this current. So the 2 volts, so if you have a battery, which is a constant voltage supply, in small signal, that's going to look like a closed switch or a short. Okay, so meaning that this guy is just going to go look like a short to ground. Okay, so I want to draw it as a short to ground here in small signal. As strange as that may seem. Okay, so, and then the base is connected to the collector in this particular circuit. So I'm going to connect them here. And then there is a resistor hanging off the emitter going to ground. So I'm going to draw that here. And that's it. So this is your small signal circuit with these values for R sub pi and G sub m. And this is the connectivity. Okay, so that's the solution to this problem. Any questions, guys?
Professor,
Go.
I have a
Go
question.
ahead.
You can go ahead.
Oh, I get IC again for step 2.
I'm sorry, can you say that again?
I'm sorry if I'm acting like an idiot here, but how you get IC for step 2?
Yeah, so that's the whole procedure we went to figure out was the crossing point between these two, is the bias point. So we calculated.
Oh, okay.
So from either the iterative procedure or the graphical procedure, but basically we solved these 2 equations and 2 unknowns to come up with IC and B, and we just really ended up using IC.
Okay.
Yeah. So, Kevin?
I just had a question about step 1.
Yeah.
So just to be clear, where you guess the base emitter voltage and you plug it into your linear function of the resistor, and you have a value for VE. That VE, if we were to plug that into IC equals IS exponential of V over VT, VBE over VT, excuse me, we would get a value that's off, like how you showed on the graphical method. So would you say that it's safer to use the first equation 1 that you have there, since it's a linear graph and there's, there isn't a big difference between the values?
Yeah.
Just because in the neighborhood of the VBE, the values disparage more than the linear one. Does that make any sense? Like, is it more safe to just use the linear equation?
Well, the thing is, in the end, you're gonna have to look at both at every step. Because look at the, let me, what the heck? Where's the other shader? Come on. Help me out. Ah, this thing keeps popping out. I don't know. Let me just share my screen. Share. So so that would be this equation, this orange equation, right, Kevin?
Yeah.
See, this thing is good. Yeah, you're right. The I sub c doesn't change very much as we pick different VBE values or VE values, depending on how we look at it. But that also means we could be off by quite a bit. I mean, you could have picked something over here or something over here. So that's fine. But in the end, you've got to find where the exponential and the linear intersect. So you always have to like calculate both at every step to see if the exponential is less than the linear or the exponential is more than linear to inform your next step. If that makes sense. I don't know if that's a question you were asking or not.
Yeah, that's exactly it. Thank you. Okay, got it. Thank you.
Yeah. But it's all, I mean, the point I'm trying to make here, guys, is that it's the gist of the problem is you got these two equations that to find the operating point, you have to solve both, these two equations. And the only way to do it is with like numerical analysis. And then, hey, if you like, maybe there's like, I'm not a mathematician, maybe there's like a whole bunch of different ways to do numerical analysis. I just know this sort of like this plug and chug or the graphical model, but basically that's what you're doing. And so the popular ones are the ones I've seen in circuit design anyway, or this sort of iterative numerical procedure that you see in the homework, or this graphical procedure that's called load line analysis. And then, there might be a bunch of other ways, but the upshot is you're trying to solve, if you've got some other way to solve this thing, and your math is better than mine, feel free. Are you guys see my, what are you guys seeing? My shared, or sharing? No, you guys are still seeing my Excel sheet?
Yeah, we still see it.
Mm-hmm.
Show that, and then share this over here. Start, yes, share. So the upshot is you got to solve these two equations, and you have to do it numerically, unfortunately. So that's this whole business with graphing and this and stuff. It's just math. It's like, it's you guys are forced into it in a circuit design class, but it's just because we have to do that math to like solve these circuit equations. It's not like some inherent circuit related, it's just a numerical analysis techniques. Okay. Any other questions, guys? So if there are no other questions, I was going to cover, I was hoping we're going to get done with this pretty quick. I always think these lectures are going to be short, and I was going to let you guys off the hook quick, which I will, but I was going to cover, yeah, Armand, you have a question?
It's not necessarily about the topic, more so about class. I can, like after class, I have a question.
Oh, okay. Is it a private question or?
Yeah, private.
So what I normally suggest we do then on is like, I'll hang up on the rest of the class and we get on the
Office hours.
Office hours, yeah.
Yeah, I got it. Okay, cool.
Okay, so well, anyway, I was going to cover another topic, which was this early effect. So, but I don't think it's, you guys are probably all burned out, and I don't want to switch topics. So I think I'm going to stop here, and then we're going to have our quiz on Thursday, first thing, and that's going to cover basically all this stuff, right? It's going to cover small signal, bipolar, these guys, right? Whatever we've covered. And then we're going to finish up chapter 4, which is this early effect, and we're going to talk about the PNP transistor, which is like another small thing. So hopefully quickly finish that off. And then we're going to start getting into chapter 5 after that. Okay. Any questions, guys? Okay.
Not for me.
Okay. If not, I'm just going to let you guys go. Let's get a whole extra 4 minutes back in your life. And I guess we'll good luck on the quiz on Thursday.
Thank you, Professor.
Thanks.
Thank you,
Professor.
Thank you, Professor.
Thanks. Bye.